Assalamualaikum and good day everyone. My name is Nurul Afika Inshira binti Abu and my student ID is 22002020. Today I will present my software requirement engineering individual project entitled LLM-Assisted Bug Report Triaging and Prioritization System for Software Quality Management. This project focuses on improving the way software development teams manage bug reports. It introduced an intelligent system that uses a large language model, semantic duplicate detection, and automatic priority scoring. The main purpose is to reduce manual work, improve consistency, and help developers identify important software defects more quickly. This presentation is divided into 9 main areas. First, I will explain the project background and vision. Then, I will discuss the current problems and the project objective. After that, I will present the system goals and the requirement engineering context. The next section covers the analysis models, including the use case, activity, and functional models. I will then explain the development methodology, purpose interface, requirement elicitation methods, and project planning. Finally, I will present the expected project output, benefits, and conclusion. Software development teams receive bug reports from many sources, including users, testers, and developers. These reports are commonly submitted through issues tracking platforms, such as GitHub issues. Each bug report usually contains a title, description, and information about the software problem. Before a bug can be fixed, the development team must perform bug triaging. This process includes reviewing the report, classifying the severity, checking whether the same issues has already been reported, and deciding which bug should be fixed first. When the number of reports increases, performing all these tasks manually becomes difficult and time-consuming. The quality of the result may also depend on the experience and judgment of individual developers. This project introduced an intelligent system because large language models can understand the meaning and context of written bug description. Therefore, they can support automatic classification, semantic duplicate detection, and bug prioritization. The proposed system aims to make bug management faster, more consistent, and more efficient. The vision of this project is to establish an intelligent and efficient bug triaging environment. The system is desired to improve software quality management through 3 main functions. The first function is accurate bug classification. The system analyzes the bug description and predicts the severity level consistently. The second function is semantic duplicate detection. Instead of matching only exact keywords, the system analyzes the meaning of the report to identify similar issues written using different words. The third function is reliable bug prioritization. The system generates a priority score so that the critical bugs can be identified more easily. As shown in the flow, intelligent bug management reduces manual work. Reduced manual work can lead to a faster bug resolution. Faster resolution supports developer productivity and contributes to higher software quality. Therefore, this project does not only focus on one bug triaging task, it aims to improve the complete process through an integrated system. This project is time-consuming manual review. When a project receives many bug reports, developers must spend a large amount of time reading and organizing them. This reduces the time available for fixing the actual software defects. The second problem is inconsistent classification. Different developers may interpret the same report differently. For example, one developer may classify an issue as critical, while another may consider it medium severity. The third problem is duplicate bug reports. Users may report the same software problem using different descriptions. Traditional keyword-based methods may not recognize this report as duplicate because the words are different, even though the meaning is similar. The fourth problem is subjective prioritization. Deciding which bug should be fixed first often depends on personal experience. As a result, an important or critical issue may be delayed or overlooked. This problem shows the need for an integrated system that can automatically classify reports, detect semantic duplicates, and recommend appropriate priority levels. This project has three objectives. The first objective is to analyze the current bug triaging process and identify the software requirement for an intelligent bug triaging system. This objective focuses on understanding the existing problem, stakeholder needs, system context, and expected function. The second objective is to design and develop an LLM-Assisted system for bug classification, semantic duplicate detection, and bug prioritization. This objective represents the main technical contribution of the project because the three functions are integrated into one system. The third objective is to evaluate the performance of the proposed system and compare it with traditional machine learning models. The traditional models include naive-Bayes, support vector machine, and random forest. The comparison will use accuracy, precision, recall, and F1 score. This objective ensures that the project covers requirement analysis, system development, and performance evaluation. The overall system goal is to improve software quality management through intelligent bug management. To achieve this overall goal, the system has three high-priority core goals. The first goal is to improve bug classification. The system should automatically classify bug reports accurately and consistently using a large language model. The second goal is to detect semantic duplicate reports. The system converts bug description into semantic representation and use similarity analysis to identify reports that describe the same issues. The third goal is to prioritize bug reports. The system generates a priority score and displays the most important bug first. When these three goals are achieved, they produce two expected outcomes. The first outcome is reduced manual bug triaging because developers no longer need to complete every analysis task manually. The second outcome is improved developer productivity because developers can focus their attention on the most important software defects. Therefore, classification, duplicate detection, and prioritization are the core functions supporting the overall goal of better software quality management. In requirement engineering, the context describes the environment surrounding the proposed system. For this project, the context is divided into four facets. The first is the subject context. This identifies the main information objects managed by the system, including the bug report, title, description, severity level, priority level, duplicate status, and repository. The second is the user context. This identifies the main users. Software developers review prioritized reports and resolve defects. QA or test engineers submit and verify bug reports. Project managers monitor bug status and progress. System evaluators compare the LLM with traditional machine learning models. The third is the IT system context. The system integrates with the GitHub Issues API, the large language model, sentence transformers, face, SQLite, and the Streamlit dashboard. The final facet is the development context. The system is developed using Python, Fast API, Streamlit, Visual Studio Code, GitHub, Postman, and ptest. These four facets ensure that the system requirements consider the users, information, technologies, and development environment.
This slide presents the use case model. A use case model shows the service provided by the system and how external actors interact with those services. The main actors are the software developer, QA or test engineer, project manager or team lead, system evaluator or researcher, and the GitHub Issues API. The software developer and QA engineer can run the automate bug triaging process. This main process includes retrieving reports, pre-processing the text, classifying bug severity, detecting semantic duplicates, generating priority scores, and storing the analysis result. The project manager can view the dashboard, search and filter bug reports, and monitor the severity, duplicate status, and priority ranking. The system evaluator can compare the LLM with traditional machine learning models and view accuracy, precision, recall, and F1 score. The GitHub Issues API is shown outside the system boundary because it is an external system. Its role is to provide bug report data from a selected GitHub repository. Overall, the diagram shows the system boundary, external actor, and the function available to each actor. Next, this activity diagram explains the complete system workflow. The process begins when the user opens the Streamlit dashboard. The user then select or enter a GitHub repository. The system sends a request to the GitHub Issues API to retrieve bug reports. Before continuing, the system checks whether the API is available. When the API is unavailable, the system displays an error message and allows the user to enter the request. This represents the error handling path. When the API is available, the bug reports are retrieved and the text is pre-processed. Pre-processing may include cleaning unnecessary characters and preparing the report for analysis. Next, the large language model classifies the severity of each bug report. Then report text is then converted into semantic embeddings. Phase researches the embedding index to identify semantically similar reports. When a duplicate is detected, the system marks the report as a duplicate and links it to the related report. Otherwise, it is marked as unique. The system then generates a priority score using the severity and duplicate information. Finally, the results are stored in SQLite and displayed on the Streamlit dashboard. User can review, search, and filter the analyzed report. The functional model divides the proposed system into three main models. The first model is bug data management. This model retrieves bug reports from GitHub issues and stores the process analysis result in the database. The second model is a bug analysis. This model pre-processes the bug report text, classifies severity using the LLM, detects semantic duplicates using face, and generates the priority score. The third model is dashboard service. This model displays the analyzed information, allow users to search and filter reports, and present the severity, duplicate status, and priority ranking. It may also provide analytical information to support monitoring and decision making. The functional decomposition makes the system easier to understand because every module has a clear responsibility. It also supports incremental development because the modules can be implemented and tested separately before integration. The selected methodology for this project is incremental development. This methodology divides the project into manageable phases. The first phase is requirement analysis. During this phase, stakeholder needs, system goals, context, and functional requirements are identified. The second phase is system design. This includes designing the architecture, database, user interface, and analysis models. The third phase is system development. The main modules including classification, duplicate detection, priority scoring, and dashboard service are implemented. The fourth phase is testing and evaluation. Each model is tested and the LLM is compared with traditional machine learning models. The final phase is deployment and maintenance. The complete system is presented through Streamlit and improved based on testing results and user feedback. Incremental development is suitable because each intelligent component can be developed and validated independently. The main tools include Python as the programming language, Fast API for the backend, Streamlit for the dashboard, SQLite for storage, Hugging Face for the LLM, Sentence Transformer for embedding and face for semantic similarity search. GitHub also supports the version control and the GitHub Issues API provide the bug report data. Moving on to the next slide. This slide presents the proposed user interface. The first interface is the dashboard overview. It displays the total number of bug reports, critical bugs, duplicate reports, and currently displayed records. It also contains a severity chart and a list of top priority bugs. The second interface is bug report management. It presents the analyst reports in a structured table. The table includes repository information, severity, duplicate status, confidence score, priority score, and the bug description. The third interface is duplicate detection result. This interface displays semantically similar report pairs and their similarity scores. It helps users understand why a report has been marked as a duplicate. The fourth interface is the performance evaluation dashboard. It compares the LLM with naive-based SVM and random forest using accuracy, precision, recall, and F1 score. The system also includes a bug report submission interface. User can enter a repository name and bug description. The system then classifies the severity, checks for duplicates, and generates a priority score. This interface provides a clear result, easy filtering, and faster access to important bug information. For this slide, the system requirements are identified using several requirement resources and allocation technique. The first resource is the literature review. It helps identify existing bug triaging techniques, current limitations, and the use of AI in software maintenance. The second resource is GitHub issues. Real bug reports are analyzed to understand their structure, language, and common management problems. Previous research articles are also used to identify common methods for classification, duplicate detection, and prioritization. Software developers and QA engineers represent important stakeholder groups because they are directly involved in bug management. A questionnaire is proposed to collect their opinion. About manual triaging problems and desired system feature. The main elicitation technique are literature review, document analysis, and questionnaire. For project planning, the work is divided between FYP1 and FYP2. The milestone cover requirement, design, development, testing, evaluation, documentation, and presentation. The estimate budget is RM300. The cost remains low because most of the tools and technology are open source. The expected output is an intelligent bug tracking system that integrates classification, duplicate detection, and prioritization. The system will automatically classify bug severity, identify semantic duplicates report, generate priority score, store the analysis, and display the result through an interactive dashboard. The system is also expected to compare LLM performance with traditional machine learning models. The expected benefits include more consistent bug classification, reduced duplicate work, faster identification of technical issues, and lower manual effort. It should also improve developer productivity and support better software quality management. In conclusion, the requirement engineering process provides a strong foundation for this project. It identifies the system goals, stakeholders, context, functions, behavior, interface, and development requirement. The proposed system aims to support faster, smarter, and more consistent software bug management. Thank you for listening.